In this section, we'll discuss how to use derivatives to assist in curve sketching. Now, in your mathematical classes previous to this, you've had some experience sketching graphs. Usually you're limited to just asking questions like, when does it cross the x-axis? When does it cross the y-axis? Are there any asymptotes? Would be a question you'd look at with rational functions, things like that. But now that we have the derivative, we have a whole arsenal of tools at our disposal to analyze the function. Derivatives tell us when it's increasing, when it's decreasing. We can use derivatives to find maximum values, minimum values, and other features. So we're going to just kind of collect all the facts that we've developed up till now. So the first one, we know that if f is continuous on some interval and differentiable at every point, then if f prime is 0 for every point in the interval, then we've got to have a constant function. That's the only way. If the derivative is always 0, then it's constant. If the derivative is always positive, then it's increasing. And if the derivative is always negative, it's decreasing. Now, we haven't actually proven this theorem. We've kind of justified it using our sense of the derivative and what it means to have a positive slope and a negative slope. In the next section, we'll be able to use the mean value theorem to show that this is actually true rigorously. So we know this, and we've also discussed the idea of concavity, though nowhere have we formally defined it. So let's put it here that we say that a graph is concave up if the tangent line at any point is below it, and it's concave down at any point if the tangent line is above the graph. So let me draw a couple pictures to see that this captures the idea of concavity, and then we'll put down the theorem that we've discussed, that the second derivative gives us a sense of concavity. So here's a quintessential concave down graph, and if we were to look at its tangent line any place, so let's look at the tangent line there, and then allow it to move around. As we can see, the tangent line is always above the graph when it's concave down. It's always on top of the graph. It never goes below it. And so that seems to be a fairly good definition of concave down, that the tangent line is above it. Like this one. And again, plot the tangent line. We can see that when it's concave up, the tangent line is always below the graph. And again, that's why that strikes us as a good definition, that if it's concave up, by definition, it means that the tangent line is below it. Though this is a great definition and fits our sense of what it means to be concave up or concave down, the second derivative gives us a good test that we can just look at the function itself and not have to graph it or graph the tangent lines to know that it's concave up or concave down. So again, we have this theorem that states that if the second derivative is positive, so if we've got a positive value for the second derivative over the entire interval, then it's concave up. And if the second derivative is negative, then it's concave down. And if you'll recall, in class, I gave kind of a sense, a way to remember this, that if the second derivative is positive, that if you're in a positive mood, then you're smiling, and so your mouth has a concave shape. But if you're negative, if you have a negative mood, then your mouth is concave down. So concave down is a frown, concave up is a smile. So putting these two together, theorem 1 says that if the derivative is positive, then it's increasing. If the derivative is negative, it's decreasing. If the derivative is 0, it's constant. So the derivative, the first derivative, gives some sense of the behavior of the function. Is it increasing, decreasing, or constant? And then theorem 2 gives us a means of how to interpret the second derivative. That if the second derivative is positive, we've got a concave up shape. And if the second derivative is negative, we've got a concave down shape. And of course, both theorem 1 and theorem 2 are asking, well, when is the function, whether the derivative or the second derivative, positive, or when is it negative? And we've been using this third theorem to discover those intervals. And it says that if f is continuous and not 0 for all x in the interval, then f is positive for at least one point, then it's positive for the whole interval. And if it's negative for at least one point, then it's negative for the whole interval. That's why when we did sine graphs, we only have to check at one point in between zeros. And again, we haven't proven this theorem. We will do that in the next section using the intermediate value theorem. So let's use these ideas to sketch a graph. So let's sketch the graph of f of x is, say, I don't know, x cubed plus x squared minus x. And we'll make our domain be, say, negative 2 to 2. So since we're going to be using derivatives to tell us when it's increasing, we're going to use second derivatives to tell us when it's concave up, concave down. Let's compute those derivatives. So f prime is equal to 3x squared plus 2x minus 1. And this, we want to know when this is 0, because that will be when it changes either from increasing to decreasing or vice versa. So this tells us that 3x, and over here will be an x. I know my multiples here are 1, and the question is, when do we subtract or add? Well, we need 3 bigger to get 2, so we'll add here and subtract. And this has got to be equal to 0. So this tells us that our critical values are going to be, well, our endpoints, so negative 2. Then we have a 1/3 from here. We have a negative 1 from here. And then we have our endpoint 2. So those are our critical values. And if I want to make the sine graph then of f prime, so the sine graph of f prime, then my endpoint, negative 2. We have our first critical value of negative 1. We have our second value of 1/3, and then our final critical value at the endpoint of 2. And so we need to check the sign between negative 2 and 1, negative 1 and 1/3, and 1/3 and 1/2. So if I say were to take the value negative 3/2 in there, I could take the value 0 in here, I could take the value 1 in here, and evaluate f prime at those places at negative 3/2, at 0, and at 1. We get that the value of f prime at negative 3/2 is 11/4. If I put 0 into my f prime, I get negative 1. And if I put 1 into f prime, I get 4. And so these signs tell us what the sign of f prime is in each of those intervals. So in between -2 and 2, it's positive, and hence the function is increasing. Between -1 and 1/3, the derivative is negative, hence the function is decreasing. And between 1/3 and 2, the derivative is positive, so it's increasing again. Now, if we want to know about concavity, then we have to take the second derivative. So f double prime of x is 6x plus 2. And when does that equal 0? That means that x has to be negative 1/3. That would make this equal to 0. So just like with f prime, we'll look at the sign graph of f double prime. So the sign graph of f double prime, we only have one place where it can change values. That's at -1/3. And so we can take values to the left of -1/3, say at -1, and we can take values to the right of 1/3, say at 0. And again, we'll evaluate f double prime at those two places to determine the sign. And so we'll look at -1 and at 0. And at -1, we get a -6 plus 2, which is a -4. And at 0, we get a 2. So now we know that if x is less than -1/3, it's going to be negative. And if it's bigger than 1/3, it's going to be positive. In other words, it's going to be concave down in this interval and concave up in that interval. And that is enough, at least to give us a general sketch of the function. We may want to have like a nice anchor. Let's graph the function. So our range is from -2 to 2. We have some spots of interest, namely where it changes from increasing to decreasing and where it changes from concave down to concave up. So that's at -1 and 1/3 is where we see those changes. So we'll mark those here. Here's -1. Here is about where -1/3 occurs, or positive 1/3, sorry. Then we have where it changes from concave up to, or concave down to concave up at -1/3. And so putting this together, again, and also recognizing that f of 0 is 0. So we have at least one anchor. We know that it's going to go through this point. It's going to, if I'm at 0, it's going to be decreasing until I hit -1. And then it's going to be increasing after that. And so going backwards, I know from there, let's put some kind of demarcations. -1/3 is where we change concavity. 1/3 is where, let's do a different color. 1/3 is where we will change our slopes, and -1 is where we will change our slopes. And so if we start our function down here, it's going to be increasing until we hit this spot, and then decreasing till we hit this spot, and increase again. And so it'll look something like this. At this spot, it stops increasing. Now it's going to be decreasing until it hits here, and then it will be increasing again. And we know at this spot it changed from concave down to concave up. And so there's some features here we should point out. Somewhere there's a max and a min. I don't know if I drew my values correct because I didn't evaluate the endpoints. I just have the general sketch. We could do a much better job. I'm just trying to give a quick example of how we can use increasing, decreasing, and concavity. So some features we're missing. We've got some a local max here. We have a local min here. Here we have what we'll call a point of inflection. A point of inflection. And then we have some global maxes and mins that we'll want to get some handle on. But again, this is just the just using the three theorems that about the derivative. That the derivative tells us when it's concave up, and or the second derivative tells us when it's concave up and concave down. The first derivative tells us when it's increasing, decreasing, or constant.